If Pythagoras had to claim for patent, he could claim for all such images and all such configurations for which the industry would pay. In the new capitalistic structures, Pythagoras could become rich. We will talk about the Pythagoras theorem, and if Pythagoras had to ask for patent or for the royalty, then he could get a lot of money and his family could become rich. Pythagoras was interested to talk everything with the geometry and relating it with the numbers. In Sanjoy Nath'S Geometrifying Trigonometry, Sanjoy Nath extends the Pythagorean way of philosophy to the concept that all real numbers are actually triangles. Those triangles are drawn on the 2D Euclidean plane, and all 2D Euclidean triangles are real numbers, and both these are true. To implement Sanjoy Nath'S Geometrifying Trigonometry on all our school days problems, or for the college days problems, or for the math olympiad problems, or for the IIT JEE, or any kind of trigonometry problems, we first have to write these things in the well formed formula format, that is for the spreadsheet like formula, such that it is a formal language to represent the mathematical expressions. Students should know and understand that whenever there is a word kind of thing written like the one, then we have to understand it as the initial line segment L. We start all our games with the initial given line segment L, and then we draw that same length L with the same kind of proportions on several tracing papers, and we will stack all these tracing papers one above another such that we can see the top view and we can see the geometry alignments which are constructed on the basis of this L. Whenever we see these kind of expressions, then we should understand that 1 star sine theta means it should be written as the L star sine theta plus L star cos theta. That means it's the Pythagorean theorem, and here this plus is a very dicey thing, it's a doubt kind of things, and because all the kind of output line segments generated from these L sin theta star sin theta are not always guaranteed that they are collinear and end-to-end fit with all other line segments constructed from the L star cos theta. That means L star sin theta will generate 16 types of symmetries on the 2D Euclidean plane, and we will get 16 tracing papers for these. Similarly, for L star cos theta, this kind of things, we will get 16 different other symmetries, and these symmetries, all of these 32 symmetries are superimposed one above another, and then we will check this plus, it is addable or not. That means which of these line segments which are constructed due to this L sin theta star sin theta are collinear and end-to-end fit with the line segments of the L star cos theta, and these well-formed formula kind of things are written in that way. And here we are seeing that on the right hand side there is a RHS, which means 1 and which is actually understood as L, that is the overlapping with the L. First of all, we will discuss on these kind of things. Here L sin theta star sin theta, which has a representative as the LEEZ, and for L cos theta star cos theta we have another representative, one such representative as the LAZ, and there are 16 types of such representatives for the L cos theta star cos theta. Let's look at the version 17 software of Sanjoy Nath'S Geometrifying Trigonometry, from where we will understand the real pictures very easily. Say LAAZ, and here L is this L, this is the given line segment on a tracing paper, and when we are drawing LA, then one line segment is constructed, then again A is multiplied, then another line segment is constructed, and the triangles are glued. And here we have already discussed one point, that is in Sanjoy Nath'S Geometrifying Trigonometry we use the bracket balancing models of writing of the things, and this multiplicative part is the GT simplex 1, and this multiplicative multiplicative part is another GT simplex, that is GT simplex 2. These two GT simplexes are interacting and then constructing the decision problems. Now, we use the BOCDMS, BOCDMAS. It is not the BODMAS. First, the bracket balancing syntaxes of the well-formed formulas are written, and then we do the calipering. Calipering is the art of constructing the triangles from the real numbers, or to do the construction of the real numbers from the 2D triangles. And to construct the real numbers from 2D triangles, we have to do the calipering. And in the similar way, when we are trying to construct from the real numbers, then we have to do the calipering. This calipering is the straightening method, the sequential straightening method that we used to do from the ancient times for the involute constructions or the evolute constructions, and find the perimeter of any curves. In these kind of things, stage wise, we used to straighten the wires, the thin wires we used to straighten slowly and steadily, and one after another pieces we used to align with the next piece, and in this way we used to unfold the whole curve, and then we used to do the straightening of the curve to construct the line segment. And this is a common way of finding the length of the curve. These problems were known from the ancient times, and this way we unfold any triangle, this way we unfold any polygon, in this way we unfold any graph, that is the GVE objects, the Eulerian graphs or the Hamiltonian graphs, or these any kind of graphs where the vertices and edges are there, where we unlock the vertices and then straighten the edges, and in this way the whole graph turns into a single line segment. And this is the art of the calipering, and we have separate videos on these calipering processes where we construct the triangle objects from the divisions operations. Divisions is the first fundamental operations after doing the calipering, and calipering is the geometric operations that is very much necessary to construct the triangles or deconstruct the triangles. Ultimately, this calipering is the fundamental operations after bracketing of the bracket balancing of the syntaxes are done, and after doing the calipering we can do the divisions. Divisions mean, in Sanjoy Nath'S Geometrifying Trigonometry, divisions mean constructions of the triangles from the two given line segments, and we can construct 4 different kind of triangles from the numerator line segment and the denominator line segment. Any expressions on the numerator side is also representing a line segment even after doing the calipering, and the denominator is also representing another line segment. And for every line segment there are the two ends, there is the start end and the end, that is the final end. There are 4 such combinations possible with the denominator line segment and with the numerator line segment. For example, for the division, when we see the denominator has the 2 end points, the start point of denominator and end point of denominator, the start point of numerator and end point of numerator. When we lift and shift the denominator line segment on the numerator line segment in such a way that the start point of the denominator line segment is placed on the start point of the numerator line segment, and then we get a caliper object which has the 2 edges which are attached with a single point, and then we connect the third line segment to complete the triangle, and this third line segment is the complement line segment actually. In this way we can arrange the start, finish, start, finish. In this way we can construct 4 different orientations, 4 different arrangements for the triangles. And division operations in Sanjoy Nath'S Geometrifying Trigonometry is actually converting any ratio objects to the triangle objects, and any irrational numbers are also the ratio objects, because irrational number divided by 1 is also a kind of considerations to construct the triangles, and 1 is always considered as the L. L is the initial line segment in Sanjoy Nath'S Geometrifying Trigonometry. And multiplication is gluing in our software simulation version 17, in Sanjoy Nath'S Geometrifying Trigonometry version 17 in this software, where we are showing that how the gluing is working. Here I again demonstrate you that when L was there, then it was nothing, then L A is done, then one triangle is constructed, another A is done on that, then another triangle is glued to it, another A is there added, then in that way we see that another triangle is glued. In this way we get the Pythagoras spiral. In the similar way, Sanjoy Nath is extending this whole thing to the other kind of spiraling. Here LAB, this is also a variety of the cos square theta, LAA is a variety of cos square theta, LAB is also a variety of cos square theta, LAC is also a variety of the cos square theta, LAD is also a variety of cos square theta. In any kind of cos square theta, we can see the triangles are getting glued and one common edge is there, and the addresses are written beside the line segments on the GT simplex panel. Here you can see the two triangles are getting glued, and when we are doing the LAA, then the angles are added, and when we do the AB, these symmetry constructions, then the angles are not added, the same triangles are getting overlapped one another. And here in the GT simplex you can see that the LAB ultimately generates the line segment which is exactly overlapping on the L. Here we can see that LABZ, and in the same way if we do LBAZ, then we can see that LABZ and LBAZ both are constructing the final output line segments which are exactly overlapping over the L. We cannot guarantee that every time we will get this kind of cos square theta, and here if we see that LCDZ, then we see the LCDZ is constructed in this way, LCCZ is constructed in this way, LDCZ is going to construct the output line segments in this way, LCDZ and LDCZ are parallel to each other. Whatever the theta are constructed, they are parallel to L, and we can generate these kind of theorems here, and it is also a deeper theorem like the Pythagorean theorem. In the same way we can say here LACZ and LCAZ, then we can see that LACZ is parallel to LCAZ, and obviously the length of the LACZ and LCAZ are same, and these two final output line segments are always parallel, and when they cut for any angle, when this cut the L, then it will cut at the midpoint of the L. LACZ always cut the original initial line segment L at its midpoint, and this is another theorem from Sanjoy Nath'S Geometrifying Trigonometry. And in this way LCDZ, LCCZ, and here we can see that LCCZ has a specific property where we can see that LCCZ and LACZ both are collinear and also overlapping for certain values of the theta, and sometimes they get detached, but they always remain collinear. This is another theorem from Sanjoy Nath'S Geometrifying Trigonometry. These are the choreography of the line segments and the choreography of the bunch of line segments, and these kind of theorems are deeper theorems than Pythagorean theorems, and because these kind of theorems were never exposed before the Sanjoy Nath'S Geometrifying Trigonometry conventions of the construction protocols were designed. For force symmetry, for everything are there. For Sanjoy Nath'S Geometrifying Trigonometry, the convention is followed as the L is the initial line segment, Z is the final line segment. Cos theta has the four symmetries A, B, C, D. Sin theta has four symmetries E, F, G, H. Tan theta has four symmetries I, J, K, M. Sec theta has four symmetries N, O, P, Q. Cosec theta has four symmetries R, S, T, U. Cot theta has four symmetries V, W, X, Y. Now, how many possible symmetries are there for the Cartesian products of the cos square theta? We can easily say that the cos square theta means ABCD Cartesian product with the ABCD. Then we will get AAAB BCBD, CACD, and DADD. Here we can write it in this way: LAAZ, LABZ, LACZ, LADZ. In this way we can construct all these symmetries and all these parameters, and from here we can find several deeper theorems. Due to the different values of the theta, we can understand the geometric natures are changing, and there is the choreography of the bunch of line segments we can see here. Now in the same way we can list all the permutations and the Cartesian products for this, and then we will see there are 16 possible varieties. Those are LAAZ, LABZ, LACZ, LADZ, similarly LBAZ, LBBZ, LBCZ, LBDZ, LCAZ, LCBZ, LCCZ, LCDZ, LDAZ, LDBZ, LDCZ, LDDZ. When we will select all and load all, we will see the choreography of the cos square theta, and those are the bunch of line segments. And if we place the tracing papers one above another, if we place the 16 tracing papers which are all constructed from the same L, and if we stack all these tracing papers one above another, then we can see the geometry of this cos square theta like things. And when we will search such things in internet, and then we understand these kind of geometries are talking about the deeper understanding about the theorems, and several use cases of such theorems are there. Say LAAZ and other permutes. Then if we go to Google and if we search for the Google search, and if we search with our image searches, say if we search with the images here, then we see the conditions like these. Say the 16 symmetries of the cos square theta, we can see the things, the GT simplex software applications which is appear to the tool of the mathematical geometry consists like to the structure in the creativity coding, GT simplex triangles and multi-GT simplex commands, permutation selectors. And these kind of images are visible for other kind of softwares also, and we can see these are the crystallographic softwares where we can see these kind of images are present, and these kind of images are present in the applications of the magnetographies and material sciences, also in the maths Olympiad problems also. Even these kind of subjects and where the design analysis of the rigid elastic coupling in the origami systems, and where also these kind of mathematical symmetries are used. And so there is a huge business for the Sanjoy Nath'S Geometrifying Trigonometry options, and because these theorems can save a lot of time, and after doing the reverse machine learning on these subjects, we can generate several such theorems where we can use very less number of tokens to generate many more number of insights. Now if we consider the sine square theta part also, say we will write only two representatives here in the version 17 of Sanjoy Nath'S Geometrifying Trigonometry. We will write LAAZ and LEEZ only, and then we will generate the permutation and the Cartesian products generations for all these cases. It says it has found the 32 variations and 16 variations for the cos square theta and 16 variations for the sine square theta. And if we select all and then load all these selected, then on the panel we can see the outputs of these GT simplexes. And when we will change the theta, that means for the different value of the theta we have to construct 32 tracing papers, and we have to stack all these 32 tracing papers one after another to understand these kind of geometries. And in Sanjoy Nath'S Geometrifying Trigonometry simulator we can do these things very easily, such that in the Pythagoras theorems, and if we want to simulate for all these varieties of 32 stacked tracing papers, then for every angle we have to construct 32 well designed tracing papers, and we have to stack all of these tracing papers one above another aligned with the common L, the common line segments. Then only we can visualize all these kind of pictures, and these kind of pictures are very much useful for the crystallography things, for the origami kind of things, and these are also applicable for the tensegrity, the truss designing, for the free body diagram designing, for the product designing, for the many kind of products. And these product designing systems are directly related to this Sanjoy Nath'S Geometrifying Trigonometry, and it has a huge application in the modern times. Thank you.